Hello and welcome back. In this video we are going to take a look at calculations for delta G. Specifically, our problem that we have here is asking us to calculate delta G naught at 298.15 Kelvin for this particular reaction. Alright, so the reaction is hydrogen gas reacting with oxygen gas to give us H2O2 liquid. Now, notice that I've written it as an equilibrium, and that's okay. We are asked, when you calculate, it's always, remember, the products and the reactants relative to the forward reaction. This is the same here. If we wanted the opposite, we would have flipped and had written the H2O2 decomposing to hydrogen and oxygen, but that's not how we have it. Okay, this is not a balanced equation. You have to make sure it is balanced because the stoichiometry will affect the outcome. And the reaction then is 2 hydrogens, 2 hydrogens, 2 oxygens, 2 oxygens. Oh, it is balanced. Well, good. Okay, next we need to look for delta G naught. That's our unknown. We are given temperature. We're given delta H. Oh, we don't have delta S. So how are we going to do that? Well, what you could do is look in the back of the book and look up the entropy of formation values for each of the reactants and products and calculate delta S. All right. I will give you the number here in a minute, but what I want to also do is to have you think about what do you expect the delta H value, the delta S value to be. Is it going to be positive or negative? Well, we're starting with 2 moles of gas, and we're going to 1 mole of liquid. So what do you think happens? We are expecting a negative or a decrease in entropy or negative value, which is actually the case. The entropy for this reaction is negative 226.3 joules per mole per Kelvin. All right, so we have our temperature, we have our delta H, we have our delta S values, and we're asked for delta G. We have the tool that we need to use. We have an equation, delta G equals delta H minus T delta S. Now we plug in, this is our unknown, delta G naught equals, delta H is given as negative 187.78 kilojoules per mole minus our temperature is 298.15 Kelvin. And our entropy value is negative 226.3 joules per mole per Kelvin. For all of you out there that keep leaving off units, this is going to really hurt you. Okay, look, here you have kilojoules, here you have only joules. So let's convert one of these we'll convert it to kilojoules. And we'll move it over 3 decimals, and this now becomes kilojoules per mole per Kelvin. And we're ready to go. The Kelvin is going to cancel, and we're going to get negative 187.78 kilojoules per mole minus the product here. It's going to be a negative value, kilojoules per mole as well. And our delta G value that we calculate is a negative 120.31 kilojoules per mole. This means at room temperature, the reaction is delta G is negative, spontaneous. All right. So that means at room temperature, the forward reaction is favored, will be spontaneous. We could calculate the temperature at which the reaction will become non-spontaneous. In other words, at what point, at what temperature would the delta G go from negative to positive? Well, that transition is involving having the delta G to go to 0, right, before it becomes positive. So if we substitute here that delta G is going to be 0, and that's going to equal to delta H minus T delta S. And we solve for temperature. We have delta H equals T delta S. Bring it to the other side so it changes its sign. And then to solve for T, we're going to divide both sides by delta S. So when we divide the delta H by the delta S values, we're going to determine what temperature you have to reach in order for the reaction to change the sign. Here we started with negative. That's the temperature past which the reaction will be non-spontaneous. All right, and we can calculate by plugging in our values here. And our enthalpy value was 187.78, I believe, kilojoules per mole. Our delta S value was a negative 226.3 kilojoules, joules per mole per Kelvin. And you can't divide joules and kilojoules. They have to be, again, in the same unit. So we're going to divide here and make this kilojoules. And now we have kilojoule per kilojoule cancels, per mole cancels. And now we have 1 over Kelvin, which is Kelvin. So the temperature then that we calculate is going to be 829.8 Kelvin. As the temperature, that's the minimum, it has to be higher than that, for the reaction to become non-spontaneous. And that kind of shows us how we would use the various concepts and the equations in order to solve different problems. The first one that I worked through is having been given the delta H and delta S and the temperature to determine the delta G value. Spontaneity of the reaction, which we did. And then the second part, I asked you what temperature. I didn't ask, but the problem that I worked was at what temperature will the reaction become non-spontaneous. And the reason I asked that is because both values of delta H and delta S were the same sign. So they're not different signs. So there's going to be a temperature impact on the spontaneity when both delta H and delta S are the same sign. And so we calculated that the sign of delta G will change at this temperature. And that, my dear students, wraps up our lesson.